amazing people, students, lovers of chemistry out there. I'm super excited to be here with you on this last part, the part 7, or the seventh part of this series that we've been talking about on how to name organic compounds. And I trust it's been an interesting experience for each and every one of you who have stuck around till this moment thus far. And in today's final episode, we want to look at the concept of the skeletal formula practice, and we also want to see how you can draw organic compound structures for their names. Now, if you notice, for a while now, we've been dealing with how to name organic compounds. We provide the structure and then you name it. But in this case, we want to do a quick reversal of the process. We'll have the name and then we'll draw the structure. So let's get into things that we have for today's video, starting off with the skeletal formula practice. Okay, that's what we want to begin with in today's lesson. All right, now so let's define what the skeletal formula is. The skeletal formula is also called the line structure, and they are a simplified way of drawing organic molecules. Now the truth is, at first it may look tricky, but once you know the rules, they become one of the fastest ways to understand and name organic compounds. Now, all through this series, you saw that how we were identifying organic compounds was by the use of symbols like CH, 3 bonded to CH2, bonded to CH2, and so on and so forth. But in this case, we want to see another method through which you can identify organic molecules, which brings us to the case or the concept of the skeletal formula. Now, what is the skeletal formula? On the screen right now, I have an example of what the skeletal formula looks like over here. All right, so the skeletal formula is a formula in which lines represent bonds between carbon atoms. Now, in the other videos, we showed the bonds between carbon atoms by doing something like this. This line here was the one indicating the bond between carbon atoms, and then you have another carbon atom bonded to another carbon atom, and so on and so forth. But in this case, the skeletal formula denotes the bonds between carbon atoms by the usage of lines throughout the structure. As you can see over here, lines are the ones that are used to denote the bonds that are occurring between carbon atoms. And then next thing about the skeletal formula is that each corner or end of a line represents a carbon atom. Now, here is what we mean. Whenever you find a skeletal formula just like this one that we have over here, each corner simply means a point where two lines meet. Okay, so anywhere you find a corner or anywhere you find an end, a carbon atom is present there. So what we mean is this: at this point you have an end, so a carbon atom is present here. At this point you have a corner because two lines are meeting from this point and from this point, so you have a carbon atom there as well. At this point you have a carbon atom there as well. At this point it is an end, you have a carbon atom there. At this point there is a carbon atom, and at this point there is a carbon atom. So now if I am to draw this skeletal structure using the concepts that we have been used to on this series, I would simply draw it like this. At this point there is a carbon atom, so it will be C bonded to another C, then we have a double bond connecting to another C, then we have another C, we have another carbon atom, then we have another carbon atom. So the next thing to do will be to fill the remaining vacancies with hydrogen atoms. So I have CH3, I have CH2, I have CH, and then I have CH3 over here. This is what this structure simply looks like in the condensed formula. So now, next thing about the skeletal structure is that hydrogen atoms are usually bonded to carbon and they are usually not shown. You can see over here this structure that we have, we did not denote the presence of hydrogen atoms. But over here, when I was making it more illustrative and visible, I showed the presence of the hydrogen atoms. But in the skeletal structure, we usually do not show the presence of hydrogen atoms. Then finally, other atoms like oxygen, nitrogen, and halogens are usually shown with their symbols. So here is what we mean. Now you can see that there is no symbol that indicates the presence of maybe an halogen like chlorine or oxygen or nitrogen. It simply means that this skeletal structure does not contain any of those. If the skeletal structure contains oxygen, we will denote the presence by simply showing the symbol. Now you can see that oxygen is present in this skeletal structure because we've denoted the presence of oxygen. So that's just how it works. Okay, lines represent bonds between carbon atoms. Each corner or end of a line shows the presence of a carbon atom. Other atoms like oxygen, nitrogen, and halogens must be shown using their symbols. So now that we have that cleared out of the way, here are some naming tips for skeletal structures that you need to have at the back of your mind. First things first, you need to count the longest carbon chain, and that will be your base name. So if we want to name this compound over here, let's count the longest chain. So we can start from the left. We have 1, 2, 3, 4, 5. You can see from this place to this place, all the way to this end, and then to this place, and then all the way to this place. We ended up with 5 carbon atoms. So having 5 carbon atoms tells us that the parent name of this compound is going to be pent. So the next thing says look for double or triple bonds and show their positions in the name. Is there a double bond in this compound? Of course there is a double bond over here, and it is on the carbon number 2. Remember, we are counting from the end that will give the double bond the priority. So this is carbon number 1, carbon number 2 over here, and then we have carbon number 3, carbon number 4, and carbon number 5. So automatically that means this CH3 over here becomes a branch. We're coming to that later. But now that we have identified the carbon that contains the double bond to be on number 2, to identify it, we'll simply use the name 2ene, showing that there is a double bond on carbon number 2. Next thing to do is to spot and name functional groups like alcohols, acids, or halogens. Now in this case, we do not have any functional group apart from the double bond and apart from the methyl branch. So next thing to do is to number the chain so that the functional group or double bond gets the lowest number. You saw that we numbered this chain such that the double bond got the number 2. So the next thing is to use prefixes for branches like methyl or ethyl. So let's do them step by step. We've counted the longest chain. The longest chain is 5 carbon atoms. So we have PENT. We've looked for double bonds. Double bond is on carbon number 2. So we have 2ENE as the suffix. And then we saw that there are no functional groups. So, and we have numbered the chain so that the functional group and the double bond got the lowest number. This is 1, 2, 3, 4, and 5. So on this carbon number 3, we have a methyl substituent, CH3. Remember, at the end of every line, there is a carbon atom. So this is the carbon atom present here, CH3, and it is methyl. So in order to identify that we have 3-methyl as the prefix, 3-methyl. So adding everything together, we have 3-methyl plus the parent name, which is pent, plus the suffix, which is 2-ene. Altogether, the name becomes 3-methyl pent 2-ene. 3-methyl pent 2-ene. That is the name of this compound. I'm sure you saw how that works. So at this point, let me make something very clear. If I wanted to draw this structure in such a way that I would show the presence of all the atoms, it would look like this: C bonded to C, and then we have a double bond bonded to another C. Then we have this line over here. then we have C, and then we have C. This part you can see stands for this part. This part you can see stands for this part over here. This part stands for this part. This part corresponds to this part. And then finally, this part corresponds to this part. So the next thing I will do is to fill up all the vacancies with hydrogens. So for here we have CH3. For here we'll have CH. For here we'll have CH3. For here we have CH2 and then CH3. That is what the structure would look like. So I just decided to do that for the sake of being illustrative. Now, moving on, we have the next structure, which is actually a skeletal structure. This is called cyclobutane because it is a cyclo compound, because it is in a ringed structure, moving around in a loop, having no end. And how many carbon atoms are present in this compound? Let's go ahead and count. Remember, at every junction where two lines meet, or at every end, there is a carbon atom. So we have one junction over here, carbon number 1, carbon number 2, carbon number 3, carbon number 4. 4 carbon atoms uses the name BUT, or the prefix BUT, but, and it is a cyclo compound. So we have cyclo plus but, and it is an alkane because there are only single bonds present in the entire compound. So we have cyclobutane as the name of this compound. Now let me do a quick trick. If I came to this point and then I attached a functional group, a hydroxyl functional group, this thing will change. Why? Because we now have a functional group which is an alcohol functional group. An alcohol functional group uses the suffix OL, all. So the name of this thing will now become cyclo plus the number of carbon atoms, which is but 4 carbon atoms, plus it's an alkane, so we use the name AN, and then now it has an alcohol functional group, so we use the suffix O. Altogether we have the name cyclobutanol. That would be the name of this compound. In the same way, if I come over here and I put a branch CH3, it would also change. It will now become methyl cyclobutane, because this is an alkyl branch or substituent, and they are always used as prefix. So ahead. Now that we've talked about the concept of naming skeletal structures, let's talk about the concept of drawing structures for their names. Now you know that thus far we've only been having structures and then we're naming them. Now in this case, we want to reverse the process where you will be given the IUPAC name and your job is to now draw the correct structure. So let's see the step-by-step process of doing that. So here are some drawing tips that you need to know. First of all, you start with the backbone. The backbone is the longest carbon chain. Longest carbon chain that contains the functional group or the multiple bonds present. The next thing is to add functional groups in their correct positions and then double check to check or to find out if each carbon makes 4 bonds. Remember, carbon has a valency of 4, which means it can only accommodate 4 bonds in a structure. So we need to check and make sure that those 4 bonds are fully occupied. So let's treat some examples and see if we can do that. Now we have the first example, the name 2-butanol. So rule number 1 says start with the backbone, the longest carbon chain. So we have the name but, which tells us that we have 4 carbon atoms. So we have C, 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 4 carbon atoms taken care of. The next thing that was said is that to add functional groups in their correct positions. So we have bu or 2-butanol as the name. Now the functional group is OL, all, and all signifies the functional group of OH, alcohol functional group, and the number on which it was present is on carbon number 2, 2-butanol. So if we start counting from the left to the right, we have 1, 2, 3, 4. If we have start counting from the right to the left, we have 1, 2, 3, 4. So we can place the alcohol functional group either on this one or on this one, depending on where we want to count from. So let's choose from the left to the right. That means this carbon atom will now carry the functional group of the OH. So let's do that very quickly. All right, so now we're identifying the OH. So now that we have done that, the next thing is to double check that each carbon makes 4 bonds. So now what that means is that we are going to fill up the remaining carbon atoms with hydrogen. All right, so now we have carbon over here. We're going to fill the remaining bonds with hydrogen, CH3 bonded to. Now this carbon over here, the second one, has 2 bonds already filled. It means it now needs one more bond from an hydrogen and then another bond that connects to the next carbon atom. So on this next carbon atom, we have CH2 bonded to the last carbon atom, which is CH3. So now each carbon atom has their 4 bonds fully occupied. This is what the structure looks like. I can draw it like this, or I can choose to draw it like this. CH2 and CH3, whichever way I choose to. Now let's do a quick let's add a quick twist to it. If I wanted to draw this in the skeletal structure, how would it look like? I would simply indicate it like this. Now at this point I have 1, 2, 3, 4 carbon atoms. Now I would indicate the presence of the alcohol functional group like this, and that will be all. So now I have my carbon number 1, carbon number 2, carbon number 3, and carbon number 4. And we have the alcohol functional group on carbon number 2. So we have 2-butanol. I'm sure you're seeing how every of this is playing out. So let's move on to another example. Example number 2, we have 3-methyl pentanoic acid. So let's go ahead and take them step by step. So first things first, we start with the backbone, which is the longest carbon chain. How do we know the longest carbon chain? We pay attention to the name pent. Pent signifies that we have 5 carbon atoms. So let's draw that. 1, 2, 3, 4, 5 carbon atoms. And then it has the suffix oic acid. Oic acid shows us that it has a functional group of COOH. So let's put the functional group COOH over here. So now that we have identified the functional group, the next thing to do after identifying the functional group is to double check that each carbon makes 4 bonds. Now remember, there is a prefix over here that says 3-methyl. So now this functional group definitely is taking the priority. So we're going to start counting from the position closest to it. So we have carbon number 1, carbon number 2, carbon number 3. So the methyl is going to be on carbon number 3. So let's indicate the presence of the methyl branch over here. So we have taken care of the methyl, we've taken care of the functional group, and we've taken care of the pent. So let's fill the remaining positions with hydrogen. So we have CH3 bonded to CH2 bonded to CH bonded to CH2 bonded to COOH. So this is what the structure will now look like. CH3, CH2, CH, and then we have CH2 and then COOH. And now if I wanted to draw the structure of this compound using the skeletal structure, it would simply look like this. So at this point I have 1, 2, 3, 4, 5 carbon atoms. Now indicate the presence of the functional group over here like this, COOH, and then indicate the presence of methyl on carbon number 3 like this. So it's just a simple way of denoting organic compounds. I'm sure you're seeing how we can derive the structure of organic compounds using their names. Now, here are some practice questions for you. And as a bonus, I'm going to be solving one of them. Okay, so let's go ahead and solve. Let me solve this one. 4-amino pentanal. So first things first, we have the backbone, which is the longest carbon chain, and it is denoted by the name pent. So we have 1, 2, 3, 4, 5, because pent denotes the number 5 carbon atoms. So now that we have that in place, let's take care of the functional groups. Now we have two functional groups, amino, and then we have Al. Now Al signifies the presence of an aldehyde functional group, and amino denotes the presence of an amine functional group. Between these two, this guy takes priority because in the order of priority, the aldehyde functional group comes before the amine functional group. So that means we're going to give priority to this guy over here. So how do we do that? It means we're going to start counting from the end closest, or we're going to attach the aldehyde functional group to the end from where we'll count. So to do that, we have CHO over here. So now that we have identified it, it means we'll start counting from here. 1, 2, 3, 4, and 5. So the next thing to do is to identify the second functional group, and it says 4-amino. So amine functional group is going to be on carbon number 4. So now that we have identified it, the next thing to do is to fill up the other carbon atoms with hydrogen. So we have CH3 bonded to CH, bonded to CH2, bonded to CH2, bonded to CHO. So if I were to draw this structure again, it would look like this. I'm sure you're enjoying every bit of this lesson. If you are, please do well to like, share, subscribe, and turn on the notification bell icon. So when more videos like this come out, you'd be the first to be notified. This is what the structure would look like. So go ahead and do the structures of all these compounds. I'd be waiting to receive them in the comment section below. Or if you'd like to engage with me personally, here is my WhatsApp contact: +234 81 20 10 78 75. You can DM me on WhatsApp and send a screenshot of what the structure looks like, and I'd be more than willing to engage with you. All right, it's bye for now. I want to say a very big thank you for engaging with me on this space. All I do here, like I say all the time, is to take the mystery out of chemistry so chemi can make history. I will see you in the next video, and in the next series definitely, where we're going to be talking about more amazing and interesting chemical and chemistry concepts.